Have you ever had a Linux server just grind to a halt? Or worse, kill one of your most important processes, even when you swear you had plenty of free memory? Yeah, you're not alone. Today, we're going to unravel the mystery of Linux memory management and its most infamous character, the out-of-memory killer. Let's dive in.
So our story really begins with this common and, let's be honest, super frustrating paradox. It's something that has tripped up so many developers and engineers. It feels totally backwards, but I promise by the end of this, it's all going to click into place.
And here it is. This is the big question, right? You run FreeAM or HTOP, you see what looks like a ton of available memory, but your application just got terminated, or the entire machine feels like it's wading through mud. What's going on? Well, this isn't some random bug. It's actually a feature, and you're about to understand exactly how it works.
Okay, to crack this case, the very first thing we have to do is just completely throw out our old-school idea of what free memory even means. Linux operates on a totally different philosophy, and once you get this, everything else starts to make sense.
This right here, this is the core principle, the golden rule of Linux memory management. See, if there's a chunk of RAM just sitting there empty, Linux looks at that as a huge wasted opportunity. It's going to aggressively put that memory to work to make the whole system faster, instead of just letting it do nothing.
So, you might be asking, where does all that free memory go? Well, it goes right here, into something called the page cache. Think of it like a kitchen pantry. Instead of running to the grocery store, which is your slow hard drive, every single time you need an ingredient, Linux keeps all the stuff you use often right there in the pantry, your super fast RAM. This makes everything feel way snappier. So that memory isn't gone, it's just being used incredibly smartly. And here is the absolute key. This is the magic trick. All that memory being used for the cache, it's not locked away forever. The very instant one of your applications actually needs more RAM, Linux will just, poof, clear out a piece of that cache and hand it right over. It's totally flexible and available. Now, memory that an application is actively using, that's different. That can't be given up so easily.
All right, on to the next major piece of the puzzle. We need to talk about the difference between the memory a process thinks it has versus the memory it's actually using. And this, my friends, is the brilliant illusion of virtual memory.
So get this. Every single process running on your machine believes it has the entire system's memory all to itself. It's living in its own private mansion. It's kind of like every resident in an apartment building having a key that's just labeled #1. Of course, that's not the real world. The kernel is the building manager. It knows the real apartment numbers, and it cleverly maps each person's #1 key to the correct physical space in the building, which is your physical RAM. This whole system lets the kernel do something really clever. It can promise way more memory than actually exists. Okay, this is a really important distinction to get. That promise of memory is called the virtual size, or VSZ. You'll see it in tools like TOP, and it can be a massive number, but most of the time it's harmless. It's just a reservation. What you really need to watch is the resident set size, or RSS. That's the amount of actual physical RAM the process is using right this second. This whole strategy of promising more than you have is called memory overcommit, and it's usually super efficient, but it does set the stage for a potential problem down the road. Just remember, RSS is the number to watch.
Okay, so we've established that Linux uses free RAM for caching, and that RSS is the real number we should be looking at. So what happens when the RSS of all our applications starts to grow, and the system comes under some real pressure?
Well, Linux doesn't just panic. It has a very calm, very logical, four-step plan. First, it does the easiest thing. It starts reclaiming that super flexible page cache we talked about, no problem. If that's not enough, it looks for some other memory pages that aren't being used much. Then, as things get more serious, it starts moving some inactive data to a much slower area on the disk called swap. And only when all of those options have failed does it bring out the big guns.
Now let's be perfectly clear about swap space. It is not more RAM. Think of it as an emergency storage unit you have on your slow spinning hard drive. When RAM gets really full, Linux starts moving stuff it hasn't used in a while into this slow storage unit. Now this is better than killing your process, sure, but it will slow your system to a crawl because getting that data back is thousands of times slower than getting it from RAM.
And here we are, the climax. The cache has been reclaimed. Swap is either full or it's just too slow to keep up. And at that exact moment, an application asks for a piece of memory that the system simply does not have. The kernel has to make a brutal choice: kill one process or let the entire system crash and burn. It chooses survival.
So let's get this straight.
The out-of-memory killer is not a bug, it's a safety mechanism. It is the system's absolute last resort, a desperate act to prevent a total kernel panic and system failure. It's designed to free up a big chunk of memory, and fast.
You know, there's this myth that the OOM killer just picks a process at random and takes it out. That is not true at all. It actually runs a pretty sophisticated algorithm to figure out the best process to terminate. It's less like a random mugging and more like a nightclub bouncer who has to remove the one person causing the most trouble to save the party for everyone else.
So why does it sometimes feel like it kills your most important process, like your database? Well, because from the kernel's point of view, that process is the best candidate. Remember that memory overcommit thing? This is where the bill comes due. When a bunch of apps that were all promised memory suddenly decide to actually use it at the same time, the system runs out. The OOM killer looks for the process that will free up the most RAM with one kill, and that's almost always a big, long-running application with a massive resident set size.
All right, we've gathered all the clues, we have our concepts in place. Let's put it all together and go back to our original question and finally, definitively, solve this mystery.
This table just lays it out perfectly. Let's look at these two classic scenarios. First, the OOM kill. When you see free memory, you now know that free memory was actually the page cache. But if a bunch of apps all suddenly demand the memory they were promised, their RSS spikes, eating up all the real RAM and the cache. The kernel's hand is forced, and it has to act. Second scenario. The system is just slow. The CPU usage looks fine, but everything is lagging. That is almost certainly a phenomenon called thrashing. The system is so low on real RAM that it's spending all its time just frantically swapping data back and forth between the fast RAM and the slow disk. It's too busy managing memory to do any actual work.
If you take only one thing away from all of this, let it be this sentence. This perfectly sums it all up. You've got the illusion of virtual memory, the smart use of RAM for caching, the calm process of reclaiming that memory when needed, and finally, the protective role of the OOM killer as the ultimate safety net.
So, let's just quickly recap the absolute must-knows. 1. Unused memory is wasted memory. Linux will always put it to work. 2. When you're debugging, watch RSS, not VSC. That's the real story. 3. A little memory pressure is normal. That's just the system balancing things. The OOM killer means you're in a real emergency. And 4. The OOM killer isn't your enemy. It's a strategic protector of last resort.
So there you have it. You now have the mental model to understand what's really going on inside your system's memory. The next time you run a command like top or htop, you're going to see those cached and resident memory columns in a whole new light. So the only question left is, with this new knowledge, what are you going to go investigate on your system first?